Ooh.
Oh,
Okay, should be on now.
I think we're on now, everybody. Welcome aboard. Hello, and it's the 3rd of March. Beware the Ides. This is our club's 209th edition of the SBAU Astro Hour, and I'm your host, Ronnie Herron. It's a weekly Monday morning blog on YouTube for the astrophysics club we call Santa Barbara Astronomical Unit. This is episode number 209, and I'm going to try to talk slower so I don't crack my voice. It is the start of SBAU's 5th year on the big screen. Our Zoom meetings, we love to get together. You guys from the club talk about our science that we love, astronomy, and SBAU is headquartered up at the Santa Barbara Museum of Natural History, where this weekend's first Friday general meeting is followed by the second Saturday star party. Our Friday general meeting starts with a free half hour in the planetarium, followed by our talk from Dr. Jeffrey Bennett, a free planetarium show, followed by our trip into space to look for extraterrestrials. Happy 5th year, guys. We're starting it today. Let me talk to everybody. Jerry Wilson, beloved president,
Good
7
morning.
or 8 years now. Jerry is married to Pat Forgy, a great supporter of her husband and of the club. Chuck McPartland is married to Pat McPartland, our outreach coordinator, and she is merchandise manager and now taking on treasury. And a lot of people consider the McPartlands the heart and soul of the club. Jerry is our commander of the starship here. Tom Whittemore is on screen.
Dobry dien.
Yep, former Westmont professor. What did you say?
I said hello in Ukrainian.
Good
Dobry
day.
dien.
Say it again. I didn't hear it.
Dobry dien.
I'd love to know it.
Yeah.
That flag's going to be behind our outreach guy for a lot of years to come, it looks like.
I hope.
It's looking good. Anyway, how's Maureen doing?
Hmm.
She's enjoying her retirement, isn't she,
Yeah.
from the clinic? And Bruce Murdoch joined us early. He's married to Bonnie,
Where's my
longtime
hand? There we
supporter. I just learned he has a 5-inch, an 8-inch, and a 10-inch. No, 11-inch.
3.5 inch.
All right. Anyway, his wife is Bonnie, and we wish her Godspeed on her health problems. So we all have our own problems. Hey, there's Tim Crawford. He's married to Karen. Hello, Tim.
Hey!
Telescope expert and a good supporter, and he's always there. And he's been with us for how many years? You've been in the club, Tim?
Oh, 1,000.
These 4 years seem to go so fast. I guess we started this podcast in the middle of the pandemic, or was it over? It was mid-March, early March of 2021. And the pandemic hit about 20.
It's still going. It was still going. In 21.
Did we ever wear masks on the screen? I guess we didn't have to, did we?
No, we're all isolated here.
Let me tell you what. Can I run down the today's talking points?
Mhm.
Lunar X, whatever that is, you're going to show us on the quarter moon. Talking points. Ryan's got a pup. His dog is serious.
It's on
And
team.
we got a great
Tim's
picture of
t-shirt,
the
Ron.
Horsehead Nebula. And our continuing look at science. This week we cover the history and the different ages of scientific discovery. I love that little series you're doing at the end there, Jerry. He is the captain, the professor, the guru, the great guru of the galaxy, Jerry Wilson. And we start with sillies, though, because we got about a half a dozen cartoons and some thought provokers sent to all of us. We'll love to share to you guys right now. Starting with the ancient shot of a woolly mammoth being peppered with spears, and it turns out to be early acupuncture. He said, that's odd. My neck suddenly feels a lot better. So that's how it started. Speaking of early science.
Uh-huh.
All right, this one I'm not sure. A guy says, oh, yes, I am. A guy says he was questioned on a plane for doing math during the flight. The lady sitting next to him, to the Ivy League economist, told flight crew she had security concerns about this man after seeing him write in a foreign script. It turned out to be a differential equation, suspected not to tie to Al-Qaeda, but to algebra. I got it. That's funny. All right. Jeff Bezos, I never saw this one. Never complained, never wanted. I think this is washed out.
Okay.
A little bit.
This is a very political. We probably was on the borderline with what I show.
Well, show it anyway. I would love to see
Oh,
it.
it just shows a statue of Trump, and all the billionaires are offering money to him.
To go up in the rocket?
No,
Just generally to get favor.
I know Katy Perry is a local girl that started her career. She's going up with, I think, the morning host on CBS, Gail King. All right, here is a milestone in human history. First person ever killed by a dinosaur. Turned out to be a security guard. One guard comes upon his body and says, it's pretty neat to be the first human killed by a dinosaur. The Tyrannosaurus Sex, give me a break. Tyrannosaurus Rex skull fell on him. Here's some Martian kids, and one of them brings home a little pet, I guess. He followed me home. His name is Rover. I'm going to call him Perseverance. And here is a Carl Sagan. Yeah, Carl Saganism says the progress of science is littered with dead theories. But the advantage of science is that scientists are willing to reject the bad ideas in favor of the good ones. You know what? It's washed out at that point. What does it say in the middle, Jerry?
That's the way progress is made in
All
science.
right. Then this self-correcting aspect of science is what I'd like to see more generally applied. Makes you wonder if Neil deGrasse Tyson has taken his place completely. He's got a different style entirely, doesn't he? He's
got
almost like a
style.
stand-up comic. He makes all the rounds of the talk shows.
Who's that?
Neil deGrasse Tyson, wasn't he?
Oh, yeah, he does. Yeah. Yeah, he largely replaced Carl Sagan in his position.
Carl Sagan died.
Yeah.
I know that, but a 17-year-old Neil deGrasse Tyson was he was a mentor to him, wasn't he, Sagan, I think?
Yeah.
yes.
Yeah,
Yeah.
he was.
All right, but here's what happened to David, the slingshot slayer of Goliath, when he came to America. Statue returned
I reported this to my wife, and she just didn't like it.
I'm sorry.
Oh, well, 3 years in America will do that to you every time. Well, gentlemen, congratulations. We're still here. And it's another one of those lumped up weekends, a lot going on. Anything we should know about Mr. Outreach, Chuck, that you might tell us about real quickly?
Telescope Tuesday on Tuesday, Hollister School on Thursday, meeting Friday, and then the Star Party Saturday, and we'll see if we have clear skies for any of them.
Yeah, good call.
All right, we're on the moon, I think.
The Blue Ghost just landed last night on the moon.
No.
This is a picture it took of its own shadow and the Earth in the distance.
Wow.
So this is the second private spacecraft to land on the moon.
And is it ours?
It's private industry.
I think it's the third. There was a Japanese one too.
That fell over?
Yeah.
Oh yeah.
No.
Yeah. Yes.
It was another one from these same folks, Firefly, that fell over, but the Japanese one had a problem too.
But I'm not sure the Japanese one was from JAXA or private industry.
It was private.
Was it? Okay.
Yeah.
How quickly we forget.
Wow.
Okay. Now we're starting it off with
A summertime object.
Yeah. Yeah.
a what?
A summertime object.
Summertime object, yeah. However, this is at 5 a.m., an hour before sunrise.
Mm-hmm.
And looking at M27, which I guess the consensus seems to be on the email I got, that this is the Apple Core Nebula.
Yeah.
Oh,
Chuck Hartman Nebula. But it's down here next to Altair, which is a bright star in the sky, surrounded by its wingmen here, Terazad and Alshane something. And then over here is Cygnus with Deneb and Saturn. And so it's roughly halfway between, little off center between that thing. So this is very early in the morning, and it's just the start of things working their way across the sky from early morning till later in the year. It'll be up in the evening time.
you know, Jerry, how I try to find M27 is by using a rectangle, using Saturn and then that wing star and Albireo. and then so it makes a rectangle.
Oh, I see. You make a
Yeah.
triangle there.
Yeah.
So yeah, this halfway along the base. So
Nope. It's got like just a rectangle with that corner
It's
star.
one corner of a rectangle.
Yeah, it's one
Mhm.
corner of a rectangle.
but wait a minute. Now there's one star.
No, Alberio, Seder, the Wing
Nope.
Star, and M27.
Alberio, Seder.
Seder.
Now go down
Now go down.
there.
No,
No, not
up
too
one,
far.
up one. There you
Okay.
go.
Oh, there.
That's it.
Yeah.
Okay, and that makes
Oh,
a
that way. Yeah.
rectangle.
Yeah. You're using this as the wing star. I was talking about Altair. and
Which is a
it's
head star.
It's two wingmen here. So I thought you meant Tarzan as the wing star.
No, I just
Yes.
make a rectangle and I never find it, but now and then I do.
Well, it's not lined up there, but Sagitta, the arrow, is a group of bright star. Well, decently bright stars there. And if you go off the tip of the arrow a little ways, then you can hit M27.
Yeah.
Okay.
Well, can I ask a question?
You just did.
Yeah, he just did.
Does modern day technology allow you guys just to type something into your technological telescope and it finds the star for you?
Depends on which scope you're using.
Yep.
Oh, okay.
I do M27 and also M57 that way.
I don't do a lot of outreach these days, but before I used to find it by star hopping and visual use, not so much by the automatic go-to system.
Yeah, this is a bright and easy to find object, so you don't really need a computerized
Matter of
system.
fact, it's the brightest and one of the closest planetary nebulas to us.
Mhm.
Now, this is a picture of M27 taken on his balcony by Bruce.
Oh wow, nice, Bruce.
That
Really? You did that, Bruce?
was taken with my, I think, 5-inch scope.
Mhm.
Did you add the color or is that what it looked like? Green?
That's what it looks like. Our eyes don't see color in dim light. The camera does.
And it's washed out a little. There we go. I was going to say
Yeah.
there was some red from
Yeah,
nitrogen too.
this is
I think they probably have, I was wondering, there's the other one you had too, which is really colorful. And I thought that they probably took 3 or 4 different shots with different filters and kind of combined them.
Well, that's how you do it.
I didn't read the details on how these pictures were made, but this is from an amateur from outskirts of a European city that complains about the skylight, stray light. But it's a good picture in a small amateur scope. And this is a picture taken by, oh gosh, I don't have my cheat sheets here. Oh, this is the VLT, see up at the top, VLT,
Yeah.
very large telescope.
And it's really blown out.
Yeah.
Yeah,
Oh, is
exactly.
it?
You can't, yeah, really blown out.
Okay.
What do the different colors mean? Which elements?
Green is oxygen. A reddish is nitrogen. Yellow is sulfur. Pink is hydrogen.
Oh, pink is hydrogen.
And how many light years across that bubble, you think?
2.
Just 2 light years?
Yeah.
You could put that whole thing in between us and Proxima.
Yeah. But it's
Okay.
made by one star the size of our sun.
Can
Oh,
you
I
see
see.
this now?
Yeah.
Okay.
Yeah, now
that's
you can
nice.
see the central star.
Yeah,
Yeah.
there's the central star right there. It's a white dwarf. It's going to end up being, or our sun is going to end up doing this. It's thrown off the outer layers,
Okay.
and I would guess this is the axis of rotation of the star.
Hmm.
So
Or
those,
it's a binary.
so those elements were being made or did get made in the explosion itself?
No explosion really, but they were made in the star. Yeah.
Yeah, slow burning in the core of the star as the star aged. Our sun is converting hydrogen to helium right now, and there's no explosion, no dramatic explosion like that, but there is fusion at the core. And later it will go through subsequent stages where it converts into other things, carbon next, and then other elements.
Yeah,
None of the really
nitrogen.
heavy elements.
Nitrogen and oxygen, CNO cycle.
My understanding is that our sun and our solar system were created by the leftovers of earlier stars that gave us the higher elements. Why aren't they in the sun already?
They are.
They
Yeah.
are, but
All right. Gravity
little of
sucks.
them, and none of them are being produced in the sun.
Right.
Right.
They're in there, but the hydrogen is in the middle under fusion becoming helium.
Yes.
Well, the sun isn't going to produce anything heavier than iron until it goes into a nova, right?
It will not produce iron even.
Oh,
Yeah, it doesn't-
Oxygen,
yeah.
But
It,
iron is
it'll run
what-
through CNO. It'll run through the CNO cycle, carbon,
What num-
nitrogen, and oxygen.
What number is iron? It's 49 or something?
26.
Oh, it's 26. So
Mhm.
all the elements above 26, the minute it collapses, that's when they're made? Just a big scrambling suddenly?
no,
Oh,
Ron.
they're made continuously in layers.
Uranium, stuff like that?
Ron, when a star makes iron in its core, that's the most stably bound atomic nucleus, and now it can't make anything heavier and without expending energy. So it makes a little bit of nickel and some other slightly heavier elements in the explosion because there's some neutron capture that goes on. But the main way of making those really heavy elements is when neutron stars collide.
Collide. Neutron
Yeah.
stars collide. That gives us radium and uranium and
Yeah,
And
gold, silver.
and gravitational waves.
Yeah.
Am I seeing some type of like the solar winds here that are compressing these gases to the outer shell here?
Yeah, they're colliding, they're moving outward and colliding with interstellar media.
Mhm.
Okay. You can almost see that. This is quite a image.
Yeah.
this is called a nebula.
Yeah, it just
Mhm.
means cloud.
Can it-
Planetary nebula. Planetary nebula.
I thought nebulas were huge spawning grounds for stars like we're looking at here.
Some nebulae are.
Yeah.
Nebula just means cloud, Ron. It's a generic term.
It's Latin for cloud.
They
This
can be
stuff
vast.
will-
They can be bigger than galaxies. They can't be bigger. They're inside our galaxy. So you're right.
Well, yeah.
Right,
To be a
okay.
nebula, the way we use the term, it has to be sort of fluorescing, and for that, you need it to be not quite that big.
And from what I understand, Ronnie, is that this central star here, the ultraviolet light from it, it fluoresces. It makes all these gases glow,
Yeah.
which is really kind of similar in all of the planetary nebulas.
But this was an explosion, or it wasn't?
No,
A nova. It wasn't.
no.
It
Oh,
just,
no.
It just sloughed off the stuff like the variable stars do.
Like a strong wind.
Yeah.
Hmm.
And Tim,
I mean,
Tim, to
it's like a burp.
follow
As
up
the
on
star
your
ends its
comment.
life, the hydrogen fusion goes out and it starts, and the pressure of the light keeps the sun and other stars at their diameter. So when that fusion goes out because it's used up all the hydrogen, it starts to compress. And finally, when it compresses, I don't know, like 30 million degrees C, then the the helium gets converted into carbon. And then the star starts to pulsate, if you will, because it's trying to get going again.
But
And
this
that's when you
happened
get
to a
the
lot of
spreading
stuff.
off of the
when,
outer layers.
yeah, when it comes to the end of all those cycles of converting things, all fusion stops in the star. And the star has, as Bruce points out, it was in equilibrium between the radiation going out and the gravity pulling in. The radiation going out stops. So now there's only gravity pulling it in. And the stuff just simply falls together and it rebounds off itself. It just slams together and then it reverses its momentum when it hits the stuff from the other side, and that's what makes it all rush out again.
Well,
If you're
is the
probably
star
there, it's probably, to our senses, it's probably close enough to an explosion to, who cares about the difference, but it's not technically an explosion.
the star in the middle that we can see, is it the size of our sun?
It's
No.
the mass of our sun, probably, but not the size.
Yeah,
Probably the size of Earth.
Yeah.
Well, no kidding, and yet we can see it.
It's
and
very hot.
not- Yes, and it's
Very
hot,
hot.
but it's not burning, it's not producing any more radiation, except it's just cooling off. It's just heat because it's leftover heat. So the star is coasting into its dark star death.
Well, why don't we see all of the many of these? Why is this a
We
rare?
do.
We do.
We do. There's stuff like this all over the universe, all over
Yeah.
the galaxy. Then
Yep.
big blobs everywhere.
There are
Okay.
probably a lot of dead cinders all over the galaxies that we can't see.
Well,
I don't think yet. There's not enough time for those cinders to be there.
yeah, it takes trillions of years for these white dwarfs to cool down into black dwarfs.
Yeah.
To the moon, Alice.
Okay, now later this week, we get the first quarter moon, which is shown here from my planetarium or my moon map software. And down in this region down here, down here, there'll be the lunar X, and we'll get to that shortly. Now,
Is
this
that also called the Tycho X, the Tycho Cross,
where's that?
the lunar cross, the lunar X?
Well,
No,
it's not in Tycho, but yeah,
Yeah.
that's what we're talking about. It happens between 2:45 and 5:20 our time.
Oh, I have a picture of it someplace that I took, but I couldn't find it.
Okay.
Yeah,
So anyway, this
Tim has it on his
is-
T-shirt.
Yeah.
Yeah. This, you can't see it here, but this is Werner.
And right above Purbach.
Yeah, right above there, up in there. That's where in the first, because the Terminator is moving this way. And as soon as the light coming in this way from the sun hits a peak of two ridges that cross, you'll see this X form. And this is a picture of Werner here. And then up here, you can see the X. It's not the best picture I've seen, but it is an
Yeah.
X.
It's usually more prominent.
I was going to say the picture I took was more prominent.
Yeah,
Yeah.
it even shows in binoculars easily.
Yep.
It's a transient phenomenon. It's not there, and then it is there, and then it's not there. So they recommend the magazine Astronomy or Sky and Telescope, whichever one I got this from. Shows that suggests you take a series of frames separated by a few seconds.
Well, yeah, it was from Astronomy Magazine, and the guy just said, take photos every 5 or 10 minutes over the course of the evening. But I mean, for us, it's happening between 2:45 and 5:20. He doesn't mention the time when it's happening at all. So that's kind of a weird thing.
That's because the time that he suggests in that magazine is always Eastern Standard Time.
Well, he
And it's
doesn't
not
mention
from our
any time.
position.
He didn't mention any time at all. See,
Oh, okay.
so people are going to be a little confused about when to do it. But
Well, if you're reading from our talking points, I cut the time out. Because
I went and looked at Astronomy Magazine, and he didn't have the time.
Okay.
He had a central time for it, I think.
Okay.
Well, is it caused by an intersection of craters?
Yes.
Yes.
Yep. Uh-huh.
There's two ridges, they're crater rims
Ridge,
right there. And they intersect.
Okay, got it.
I had a really great story, Ron, when I was doing a star party at the museum years ago, and a little kid ran into what I used to call the cubby hole, and he said, "Did you see the X on the moon?" And I said, "Are you telling me that they're playing tic-tac-toe on the moon?" And he said, "Yeah." And I said, "Well, who's winning?" And he said, "The O's."
Those
You're right.
definitely are.
It was great.
It's Hollywood Squares up on the moon. I love it. Great
Okay, now
story.
we're going to take a look over in a winter constellation area that's getting close to the setting. This is 8 in the evening, and we're looking at Orion here because that's easy to see. The moon is starting to pass through on whichever day this was.
Monday.
March 3rd today, yeah. So, but we're going to look down here at Sirius, the dog star, because we're going to take a look at the pup, which Sirius is a binary star, and it has a small companion that's a challenge to see because of the brightness difference. And
Oh God.
We're going to see it.
so this is Sirius B.
There it is.
This is Sirius A. Now this is 10 seconds of an arc, so that's roughly 10 seconds of an arc there. Now,
Oh,
that's not a challenging size all by itself in our small amateur telescopes. But because of the brightness difference, this is a big deal. So,
Tommy, you said you saw this once, huh?
Not that one. I've seen the companion to Antares.
Antares.
I've never seen this one.
Oh, okay.
as an aside, I read that the companion to Antares was once claimed as the only green star in the sky because of an optical illusion. It's the way your eye contrasts the white star companion with the very red star Antares.
That makes
So,
sense. That makes
It's an
sense.
optical illusion. Apparently, there are no green stars, actual green stars to our eyes in the sky.
Yeah, we saw this in a 7-inch or 7-inch was a Starfire, Chuck?
Yeah.
This F9, 7-inch F9.
Yeah.
We were building the observatory at Evergreen Valley College, and we wanted to test, how good the sky was. And so we borrowed a 7-inch F9 from Rich Newshafer, who was a member of my old club. And we saw it. We saw it, San Jose.
Wow. The little star orbits the big one.
Yeah, Jerry's got a diagram there.
I
Oh,
can
wow.
see.
I see.
Yeah, this is Sirius A.
Oh, wow.
The whole thing together is Alpha Canis Majoris. And this is the orbit of the pup around the star as viewed from our point of view.
Wow.
So right now it's 2025, and you see it's about 10 arc seconds down here. This is 3 arc seconds across.
Well, if you're going to see it, now's the time, huh?
Yeah.
Yeah.
Together they make Sirius.
Although we're not going to have good seeing for a couple of days here.
Yeah.
Now, in this case, this has got 4 diffraction spikes on it. So it means it's got some kind of a Newtonian or Cassegrain system.
It's a 20-inch Cassegrain. It's in the data there.
Oh, thank you. Yeah, 20-inch Cassegrain.
Yeah, F9.
Good resolving power. If you get this where the diffraction pattern interferes with the star, if you can rotate the tube of the telescope so the diffraction spikes move up here, and then you're looking at the star between.
I see.
Between the diffraction spikes.
Yeah.
Some scopes use circular spiders to hold up their secondary, and the idea is that it doesn't produce diffraction spikes of any kind. It spreads that same diffraction light out over the whole field of view. And the better, for fine detail, the better scope to use, in my opinion, is a scope that produces these linear spikes, and you rotate the spikes out of the way. Because here, this area outside the spikes is darker than it is with a circular spider.
Jerry, wasn't it Barnard who first saw this? E. Barnard? Does that
I don't
sound right?
recall that. I don't know. You may be right.
It was somebody at the U.S. Naval Observatory with the Clark refractor when they first got it.
Okay.
Huh.
Well, if you use a Schmidt Cassegrain, you don't get diffraction spikes, right?
Yeah,
That's
but
true, because there's a piece of glass holding it up.
Right, exactly.
yeah, you do have a bigger central obstruction relative to the size of the scope, though.
Right.
So someone mentioned the other scope, the 12-inch scope at Naval Observatory.
Yeah.
That's also the scope that they discovered the 2 moons of Mars with.
It's a Clark refractor?
Yes, a 26-inch Clark refractor.
Yeah.
Oh, wow.
I think that's all they made, Tim. That's all they made.
Well, yeah, that's all he made. Can I make a comment on that optical illusion, if you wouldn't mind? It's an experiment you can try at home. We did in dentistry. Is that you take 2 circles and on a white sheet of paper, fill one of the circles with red, and then have a person stare at that red, and then after about half a minute to a minute, go over to the one that's unfilled with a color, the one that's just white, and you will see green there.
Yeah.
Yeah.
It's something you can do at home. It's just amazing.
Yeah.
Yeah, your eye gets saturated on the color you stared at, and then it's
Yep,
trying to
that's it.
balance by adding in the color you are illusioned by.
It goes just to the opposite side of the spectrum. Just
Yeah.
goes right, or the color wheel.
Color
Now,
wheel.
anybody know why it's called the dog?
It's the heart of Canis Major, the
Yeah,
big dog.
Canis Major.
And that's a dog constellation?
Yeah.
That's
Yeah,
Latin
oh, yeah.
for the big
Canis is
dog.
dog. Latin for dog.
All right, this is a horse nebula, not a constellation.
This
Horses,
this
It's
is
a
an
dark cloud.
example of a dark nebula in Orion.
It's just off the last star in his belt.
Yeah, it's
Yeah.
right. This is the belt right here, and right off there where the index finger of the hand is, that's where the horse head is. We were just down here looking at Sirius.
Yeah, that's one thing Barnard definitely saw. Yeah, B33.
Yeah, he has a whole series of a catalog of dark nebula. Now, this is a dark nebula in front of an illuminated, a bright nebula. And you get light down here that's reflected off the nebula, and here you get light that's stimulated to be emitted by a bright star, flooding it with X-rays that give you this luminescence. So, and then in front of it is this finger of a nebula that is not illuminated directly by a star or by its own luminescence. And so it's in front of this other nebula in the background.
And Tessa got a fantastic picture of this at the last Westmont Public Star Party.
I was going to mention that, Chuck. That it was just phenomenal.
What was she using?
Sea Star.
The
Sea
sea
star.
star, and
Yeah.
she used
15
some.
millimeters of aperture. It used to be the advice on seeing the horse head was 14 inches of aperture and clean optics.
Yeah, clean up.
Yeah, it
But
was
that's-
really
yeah.
amazing. She had some filters she put on it, or
No.
something that
No, just software processing.
software. Yeah, it was unbelievable.
I'm amazed they haven't started calling this the Godfather Nebula since it's a horse's
Yeah.
head.
Oh,
Yeah.
Pictures of that in infrared are, you look right through it, almost.
Yeah. You see all the stars inside of it forming.
Yeah, yeah.
Now, I've sketched some stuff in, what did I use? Anyway,
Going to science now.
yeah, we talked about the process of science earlier last week. And I had put together this little schematic of the ages of science. And this line here between what I call the Dark Ages and the Age of Enlightenment, this is the period in which Galileo and Kepler, with his three laws, people started transitioning from empiricism, which is just measuring. Tycho Brahe, in his Uranometria, what is it, the name of his observatory?
Urania Borg.
That's it. He had a giant, this was pre-telescope, and he had this giant instrument called a quadrant, and he used it very carefully to measure the position of stars. And when you just notice the position of stars, but you don't know what they are, you just measure what you can see. That's what I call empiricism. And it's the first, this is beyond naming constellations after mythology. But that empiricism, which built up this large body of knowledge that was used by later astronomies, and using mathematics and number systems developed in Arabia with the concept of a zero, that allowed us in Western Europe to have a place-centered, or a position-coded number system, which is key to doing science. And for example, my favorite quote is, "You can't do astronomy with Roman numerals." So
Yeah.
anyway, those two came together, and that's in the Age of Enlightenment. This is where classical physics started. So here, from Galileo's observations with instruments, the development of that instrument, and then largely Newton and other people contemporary with Newton that co-developed calculus and Newton's three laws of motion, that really was a description of what I consider our directly observable universe. That is, you could tell that the moon is going around the Earth. I'm loaning count, or what is it, Copernicus in there too. So, but he could describe the motion. So this is the first time when we're starting to get mechanisms of why you see what you see. Here, everything is done on belief and observation. And belief, while it is very frustrating these days, it's a natural process with people because it's our unconscious method of doing calculations based on an extreme paucity of information. That is, if you look at a bush, you will actually see, or your imagination will see, for example, a lion behind that bush. And even though it's not there, you're putting together teeny little bits of information that think, it might be there. And because that signal processing that does that, it imagines things that aren't really there. It comes down on the safe side. It's a false positive, but false positives keep you alive. And beliefs are, according to a book, Homo Deus, I read, beliefs are the ability to believe in lies, is what human beings developed. And it's in a universe where we don't understand the mechanisms of things. Belief is a system that people have developed to deal with the world. Something that people don't like and haven't gotten used to is deductive logic from the science that develops. They have belief systems and they don't like to go through an intellectual process of filtering the belief system for what's right and what's wrong. Remember, when we believe things, we don't believe things because they're right. We believe that they're right. So for classical physics, that was in the 1600s, and we still use that. Modern science has not contradicted classical physics. It has shown that classical physics is a special case of modern physics. But we still use classical physics unadulterated, developed by Isaac Newton and published in 1680s, to put our spacecraft on Mars unerringly. We put things in orbit using his laws. He's not wrong. In that realm of what we can directly observe, he nailed it. But then we developed instruments that can explore regions that are really much bigger than what Newton dealt with under the apple tree, and much smaller than what he could see squishing ants. So we have developed theories of relativity and cosmology for the really big stuff, and the really small stuff goes this way. Now, people with beliefs, they try and add their belief to evaluate these situations, and belief doesn't apply in these situations. It only applies where you can observe the cause and effect. Here we have to rely on mathematics and deductive reasoning to look at what is there. Our instruments can test these theories. And in the case of Einstein, with his really big stuff, relativity and cosmology, Einstein nailed it. His general relativity is the way things that is a true theory. And quantum mechanics of the very small subatomic stuff is a very real and proven theory also. They don't match each other very well, although there are some really promising works that are trying to unite these things. One of them is string theory. Ichio Kaku is a very big proponent of string theory. But there's other things like
Loop quantum gravity.
Yes, I'm trying to think of the guy that Tom Whittemore was friends with over here at the university that passed away.
Oh, Jim Hartle?
Jim Hartle and Stephen Hawking.
Stephen Hawking,
they have a theory called the no boundary proposal, which does unite these two things. The only drawback to that theory is it proposes the existence of imaginary time, and that confounds people. What the hell does imaginary time mean? But there's a lot of things that have been proposed to make theories work that were subsequently found, like neutrinos, for example. So That may be only a drawback for the present. There are other ways of doing this. I know that, for example, Einstein was so enamored with relativity and gravitation being due to the curvature of space-time, but that couldn't account for quantum mechanics. So he tried to unite the two by doing the mathematics of quantum mechanics somehow coming, and quantization somehow coming out of the twisting of space-time. So he tried to work through the twisting effects of our space-time continuum. Now, the general relativity, there's 10 equations that describe the curvature of space-time in general relativity. And that math is pretty hairy. So the math trying to understand the torsion of space-time was just apparently beyond him. He died leaving it an unsolved problem. But very interesting stuff if you read a lot of that. So this is definitely counterintuitive. The phrase in physics that I heard was, yes, your theory is crazy, but is it crazy enough to be right?
Okay.
You talked about imaginary time. Is that a quadrature to real time?
I don't know. But imaginary time is also used in quaternion dynamics. And if you're doing spacecraft orientation, you think, when you're new to the field, you think, oh, I'll just use what's that rotation in space, in real space? Euler's rotation. Thank you, Bruce. And but you can get, with real systems, they have an ultimate resolving power in how they can do commands in spacecraft for orientation and pointing. And you can get a phenomenon called gimbal lock, that you can get it pointing somewhere and you give it a command to point somewhere else. And because of the resolution of your mechanical parts, that it comes out to a non-unique solution, and the thing can't orient. So all of the spacecraft orientation are done using quaternion dynamics, which uses imaginary space. And it's also called, in physics, it's called spinors, if you came to it that way, SPINORS. But that's what we use in orientation of spacecraft. Now,
Can I ask one quick question?
yeah,
When did astrology kick in? During the blue on the left, the Dark Ages, or what, did it come along with the Age of Enlightenment with their
No,
interpretation?
it's
These weird-
ancient stuff.
What?
It's ancient stuff.
It's very old.
They knew about the zodiac way back in the Dark Ages?
Well, you can see the planets, Ron, and you watch where they go. That's the ecliptic, and the constellations along that are the zodiac.
But we discovered the planets mostly during the Age of Enlightenment, didn't we?
No, the planets are naked eye visible. They go back forever.
And they
Really?
would plot the planet location with respect to the fixed star field, and they would wander. They would go back and forth.
It means wanderer, planet.
Wanderer.
So there were 12 houses or 12 zodiac signs way back in the Dark Ages?
Yeah,
Oh, yeah.
way before that.
Yeah.
I'll be damned. I thought that came with the Enlightenment.
No,
Oh,
that's,
no.
that's
no.
disenlightenment.
The 12 months of the year, and I didn't think they discovered
that's all
Uranus.
because of lunar. That's lunar calendars giving us that mostly.
Yeah.
Okay. Well, it's still very much alive today, those idiots.
there is not, that goes way back under belief systems. Someone just made it up. And other people, oohed and awed, so they just kept making it up.
A lot of people read their horoscope every day.
And they get money for it.
Yeah, they sure do.
The strange things that the theory of relativity, going to the really big stuff, is that you assume time is the fourth dimension, and that comes out of the equations. And the light speed remains constant, no matter what speed you're doing. Light speed is always, in that frame, it always looks like it's 3 times 10 to the 10 meters per second. The faster you move through space, the slower you move through time. So our motion is actually a rotation in space-time. Gravity is the curvature of space-time. and time slows down around heavy objects. This is a scene from the Interstellar movie where that was the main plot driver. And gravity travels in the form of waves. This shows two neutron stars colliding and the waves that it produces. It doesn't produce dipole waves like electromagnetism does with opposite charges, because there is no opposite charge that we know of to gravity. So this produces, what is it, quadratic waves? No, anyway, it produces the next order higher of oscillation. And because our space-time can support these waves, that indicates that space-time itself is an elastic material, a material we live in it. It's not nothing. It's what we perceive as nothing with our senses, but it's not nothing.
It's the ether.
Ether, the way ether was defined back in the 1800s, it has been disproven.
I know.
Concept of ether.
Maxwell.
What's that?
Maxwell. Maxwell, James Clerk Maxwell.
Well, Michelson and Morley, their experiment.
Yeah, Michelson Morley experiment.
Dismissed it.
Oh, yeah, right. I forgot about that.
And the really small stuff, where every particle is a wave and a particle at the same time, at least at the way we perceive it. Let's see, what was the point I'm saying? One way of thinking about it is like you're sitting on a stream, a mountain stream, and you're fishing. And out in the pond, out in the stream, you can see this wave on the surface of the water moving toward you. And you're very quick, and you get your net and you scoop the wave up, and in the wave is a fish. So that is a wave and a particle at the same time. So there's
Sounds
a lot
kind
of
of fishy
theories.
to me.
Yeah.
There's a lot of theories about trying to reconcile these two dichotomies. And that one, what I just illustrated, is the pilot wave theory. But it really is a probability theory. The electron really doesn't have a size. We know there's a cloud that's a probability where you're going to find it. And that's about all we really know about it.
It has a charge.
What's that?
It has a charge.
Oh, yes, it has a charge. Yes, in that space we can find it.
1.602 times 10 to the minus 19th coulombs.
Okay, now if you'll bear with me here for a moment. Oh. Whoops. Okay. Let's see.
Well, can I throw something in real quick?
Go ahead.
That LIGO detector down in Louisiana and possibly the one in Washington did detect a variation, a gravitational wave of two colliding, well, I guess, black holes billions of years ago. And they figure the laser moved about the size of the middle of the electron, the nucleus, which isn't much of a wave because it was so long ago and so far away. If something like that happened to really shake the LIGO, it would probably shake us too. The gravitational wave.
It did.
It
the
did.
one that went through here did.
Yeah, I didn't feel it.
Yeah. I didn't feel it either, but you know, it's very minimal. There's not a lot of gravitational waves, it looks like, going on in space.
No, there's lots. There's a whole background buzz of them.
Right.
Well, then they're seeing them all the time.
They're in the noise of our detectors.
Yeah.
Right. And Ron, the delay time between the excitation they saw at, in Washington State and then the one down in Louisiana with speed of light. It was the speed of light.
Yeah.
Speed of light? What does that mean? I don't know.
Gravitational waves move at the speed of light.
Speed of light.
Oh, I know that, but the one they found that was so revolutionary was only the size of a nucleus of an atom.
Size of a proton.
It's a thousandth of the diameter of a proton. The motion they're detecting is like the thousandth of the diameter of a proton. It's just amazing what they've been able to do.
Well, I know, but that's very little of a jiggle.
Yeah. And Ron, there's also a detector set in Italy called Virgo.
Yeah.
That looks for these things too.
And there's another Japanese one, I think, that's coming online soon.
Yeah, we'll get a handle on these.
And we've seen lots and lots. It's not just one wave that we saw, Ron. We're seeing them all the time now. We're seeing
Hey,
mergers of
okay, I
neutron
think I got
stars,
it now.
mergers of black holes.
All
Okay,
right,
hang
Mr.
on.
Mr. President, are you taking over again?
Yep.
Oh, well, who the hell is that?
Leon Susskind.
Oh,
Oh, it looks like it's,
looks like Rupert Murdoch.
there's no sound there.
The world was governed by what is called classical physics.
Wait a second.
Amanda, what are you doing? I thought you left. You ever heard of quantum physics?
Yes, I don't know what they are.
Would you like to?
Sure.
For a long time, the way that we understood the world was governed by what is called classical physics. You know what that is?
Kind
It is a basic way of measuring and predicting things. Then along came people like Albert Einstein. Have you heard of him?
Yeah.
You know, he started to look into really small things like atoms, subatomic particles, waveforms. And it began to look like classical physics didn't apply anymore, which is mysterious, not predictable in ways we currently understand. For example, the same thing can be in two different states at the same time.
Interesting, because that wasn't really Einstein.
Particle. There's a world in which that particle is black and a world in which that particle is white. And there's a kind of point of liminal space between those worlds where the particle is black and white at the same time. And they don't seem to want to decide which state they'll be until someone looks at it. Well,
When is she gonna go? Oh, sure.
Thanks, Dr. Wizard.
What are you smoking? Yeah.
Yes, I don't know what they are.
Would you like to?
Sure.
You're gonna have to repeat a lot of that, Jerry.
Oh, you couldn't hear it well?
It was bassy.
And there were subtitles though, so
Yeah,
Yeah.
Oh, I didn't see them.
that was Leonard Susskind, a professor of gravitation and cosmology at Stanford University.
Yeah.
I took a course in general relativity from him about 5 years ago on the internet. Brilliant man, wonderful insights. He concludes, he agrees with the young girl. She says, "That's nuts." And he says, "Yes, that's nuts. Real."
What's nuts? The classical?
No,
no.
not the classical.
Relativistic.
The things that the general relativity, that the quantum mechanics predicts are things that you learned in school can't be. For example, a particle can be in two different places at the same time. A particle can go from point A to point B without having traversed the distance in between them. So these types of things are just nuts, but they're real. We can build things on them. One of the things is the quantum entanglement, which Einstein's understood as spooky action at a distance. And it does not break the law of sending information faster than the speed of light. It determines, because you look at a pair and you let them collaborate together, then you separate the pairs. And this has been done as far as orbit, from down on the Earth and up in orbit. And then you look at one, and now you know the state of the other one. And they look at that one, and that's right. So they do affect each other over any distance. It's not instantaneous travel of information as science fiction would like you to believe. But it is a very mysterious thing. There is one theory now that I lost the whole train of thought. Too much in my brain.
But this entanglement only exists in the micro world. You never have
No,
two
no,
stars
no,
connected.
no. They've entangled physical, visible size chunks of stuff.
Visible, really?
Yeah.
In the macro world.
Yes.
Stuff we see out there will
It's
entangle.
much harder to do. It's much harder to do the larger something gets, but it has been done.
And are they wormholes in between?
No.
That's where I was going with it. The one theory is that the wormhole, that when the universe was created, there were a lot of, and I mean a lot of submicroscopic wormholes, and those wormholes are actually the strings of string theory.
Hmm.
Now that is a hypothesis these days. There's no math to back it up, but you might say it's on the whisper on the street. It's one of the things that's actively being pursued, and there's a lot of really interesting stuff being pursued.
And Ron, you can find a wormhole in an old apple.
Yeah.
It's worse than finding a worm in your apple.
Yeah,
Finding half a worm,
half of a
half of a
This-
worm left.
This washed out.
It's not too bad.
Okay.
Official name. Oh, Almiaz. You see
Yeah,
that's-
it's a star, Almaraz. It's also known as Epsilon Auriga.
Okay.
It's a magnitude 3 star, which you can see with the visible eye or naked eye. It's 3,000 light years away. It's a supergiant, yellow-white. Let's see. Multi-system, yes. Variable star, yes. Exoplanet, no, but a massive debris field. What it is probable theta supernova. It's a variable star, and it is a binary system. Now, this is an artist's rendition. It's not a picture from radio telescopes or anything like that. So here's the supergiant star, the one we primarily see. Here's its small companion with a massive ring of dust around it, sort of a pre-planetary dust ring. And this thing, because of the orbit, this dust ring occults this star, passes in front. It changes the amount of light
Velocity.
from it.
Yeah.
And this is, for example, this is a real image with radio telescopes of the giant star, red giant, taken on December 2008. This is on November 3, 2009. You can see the dust cloud protruding into the way. And then here at December 3rd, 2009, it's more in the way. So this is where it is in the sky. It's an unusual variable because it's very long term. Because that dust cloud is very big, the lower, the dim part of the phase is very dim. It's very structured, and that confused people for a while. But near Capella, this is the star, Almaz, and these two are called the kids. And either this is the kid also, or this is the kid's mom or dad or something. I forget the lore that goes with that. So this is where it is in the sky. This is Orion over here on its side, Camelopardalis. This is up here in the Ursa Major and the North Pole area, the polar region, Polaris. And here is Auriga. And this is the star here, Almaz. And these are the two other kids. So I have in the, this is a nice picture taken of that too, showing how to get to it from
Way out there.
Dipper.
That's the Dipper.
Yeah. Whoops. Okay. So anyway, I had captured a nice bit of lore on the naming and the mythology of it and stuff, which I thought you guys could resonate with, but I don't have a picture of that. So you can read that at your leisure.
And that cloudy companion is rare to see. They don't have often stuff like that around a star.
Well,
It's the alignment that really makes it special. The fact that
Yeah.
it passes along our point of view.
yeah, we see a lot of stars with planetary disks, and we have a lot of radio telescope images of the and even visible light with visible optical telescopes of disks around big stars, like Fomolo, I think, has one of these big disks,
Yep.
if memory serves.
So it's
They're
slowly
not
making.
uncommon, and this is the planetary formation phase of that star system. But this star happens to be also orbiting around this gigantic supergiant star, and its disk is doing this complex occulting of the light. When they measure the light curves of it, it took a long time for them to figure out that this is what was happening.
Science thinks the sun part gets made first, and then the rest of the system. We came after the sun was made, our planet.
Big objects form first. The sun formed
Got
a
it.
dark cloud, then Jupiter formed, then all this other little things formed.
Well, we can't classify that cloud as exoplanets yet, can we?
It's a protoplanetary disk.
Wow. The things I learned, gentlemen. Gonna get ready for a big weekend. Thank you. We've reached noontime, and that is it, I guess, for SBAU's
Holy cow,
Astro Hour.
that went by fast.
Yeah, it
Yeah.
did. I learned a lot. I like the science series. That's number 209. Welcome to the 5th year of broadcasting on the radio. Give me a break. Old habits. So Friday night, we'll see you at the museum, Fleischman Auditorium, and then Saturday night, the Star Party, and we'll be back here in our living rooms next Monday morning for number 110 or 210 of the Astro Hour. Thanks, everybody, on behalf of the gang.
Thanks, Ron.
Right.
Thanks.
Take care. Love it. Beam us down, Scotty.
Beam me up, Scotty. There's no intelligent
beam it
life
up.
down.
Jerry's not moving. Are you okay, Jer? It's just me and Bruce now, taking us out one at a time, Bruce. Help.
Yeah.
I'm going.
Well, I can turn my cell phone
Well-
off and then I'll go away.
Well, I guess I'll hit mine too. Okay. Hit the little red X. Die.